Hello everyone, I will now present our first place solution for the PVUW Challenge 2024, Complex Video Object Segmentation Track. Our team is from Pingqing Laboratory, Harbin Institute of Technology, Shenzhen, and University of California at Merced. Video Object Segmentation, VOS, focuses on tracking and segmenting target objects within a video sequence, beginning with mask annotations in the initial frame. This technique has significant potential across various applications, especially given the increasing volume of video content in areas such as autonomous driving, augmented reality, and interactive video editing. The current VOS task faces several major challenges, including significant changes in target appearance, occlusions, and identity confusion due to similar objects and background clutter. These challenges are particularly pronounced in long-term videos, making the task even more complex. VOS methods generally achieve video object segmentation by comparing the test frame with previous frames. They begin by employing an association model to generate pixel-wise correlated features between the test frame and target templates. These correlated features are then used to predict the target masks accurately. To handle variations in target appearances over time, certain methods incorporates a memory module that stores samples of the targets as their appearances change. Additionally, recent approaches like QT and ISPOS introduce object queries to differentiate between various target objects, thus mitigating identity confusion. The MOSE, Complex Video Object Segmentation, Dataset is a comprehensive collection designed to provide complex and challenging scenarios with occluded and crowded objects. Unlike existing datasets that feature relatively isolated and salient objects, MOSE focuses on realistic environments, highlighting the limitations of current VOS methods and encouraging the development of more robust algorithms. This dataset is crucial for advancing VOS technologies to perform effectively in real-world applications where object interactions and occlusions are common. We propose a robust semantic-aware and query-enhanced video object segmentation method. In this solution, we first introduce the proposed fusion block, which utilizes the semantic and detailed information of the pre-trained VIP models. This helps us deal with complex target appearance variance and ID confusion between targets with similar appearances. In detail, we fuse the information of the CLS token from the VIT to multi-scale features and conduct local fusion between frame patches and multi-scale features for detailed fusion. In addition, to ensure the target representation of the target queries, we develop a discriminative query representation module in the query transformer to capture the local representation of the targets. We note that updating the target query memory directly with entire object patches generated based on online predicted masks is ineffective, as the predicted masks often cover background noise, reducing target distinctiveness and leading to accumulating errors over time. To propagate target queries effectively across frames, we update the target queries with the most distinctive feature of the target object, in detail. We select the discriminative feature of a target object by comparing the target query with every channel activation in the correlated feature map of the target and taking the most similar one. Based on the discriminative target feature generated from a new target sample, we can update target queries by dynamically calculating the relationship between the salient query and salient pixel features in an additive manner. The proposed discriminative query generation scheme adaptively refines target queries with the most representative features, which helps deal with the challenges of dramatic appearance variations in long-term videos. To enhance the model's expressive capability, we trained it on ISPOS, Davis, OVIS, Burst, and MOSE datasets. Unlike QT, we did not train on static images. The table showcases the performance of our method. During our testing, we found that input size and image flip augmentation significantly improved the model's performance. Our final version is the result of multi-scale fusion. Our method ultimately achieved first place on the MOSE test set. Next, we will showcase the results of video object segmentation in 3 different scenarios. In the MOSE dataset, inconspicuous small targets, especially parts of the given target in the first frame, are very common. In such cases, our model can effectively track and recognize the entire target. In complex and crowded scenes, the movement of targets poses a significant challenge for accurate tracking and segmentation. In this type of scenario, our model also performs exceptionally well. In heavily occluded scenes, our model can also identify the tracked target among similar objects and segment it accurately.